regulatory issues. Today, he'll talk about the intersection of new technologies and environmental regulations related to oil field methane emissions.
Okay, well, thanks, Drew. I'm just going to get myself set up here. And slide number 1 should be on the screen. That's just a picture of me. I'm Robert Kleinberg. I live in Cambridge, Massachusetts, about 3 subway stops from MIT. So I'm having this virtual conference saves me a round-trip subway fare. Otherwise, I'd prefer to be there in person. As Drew said, what I'm going to talk about today in the next half hour or so is technological innovation and environmental regulation, methane emissions from oil and gas facilities. Now, I'd like to thank Murray for really doing a very able job of introducing several aspects of this topic. That makes my job a little simpler. But I'd just like to put my talk in the context of this conference. And it's an A+B conference. And I would say that methane emission control is securely in category A, which includes minimizing environmental impact while maintaining extreme productivity. Now, natural gas is used in many segments of our energy systems, and it will be needed as we scale up our intermittent renewable energy sources as rapidly as possible while maintaining reliability. I'm going to talk about that in a minute. Another precept of this conference is that when a house catches fire, firemen must run to the closest hydrants and stop disputing which water stream would be purer. In that respect, controlling emissions of natural gas is the quickest way to mitigate global climate change, and I hope to convince you of that in a couple of minutes. Now, the good news here is that technology is advancing rapidly. The bad news is that we have a US regulatory regime which discourages new technology. Now, as of yesterday, the Environmental Protection Agency has promulgated a new set of rules on methane emission control. I will comment on that briefly at the end, but the new rules don't substantially change that conclusion, unfortunately, although in certain respects they help. So I'd like to talk about really the essential role that natural gas is going to play in our renewable energy transition. And what you're seeing here is a graph. Horizontal axis is the last decade in years from 2010 to the present. The vertical axis is the amount of energy that's stored in our natural gas system. And natural gas can be stored in big underground caverns for as long as you want. Natural gas, methane is the prime component. About 95% of natural gas is methane, is obviously stable, can sit in underground for millennia, actually, as we know, because that's where we get it. And right now, our storage system constitutes about 1,000 terawatt hours of energy. And every winter, we draw down about half that. We use up about 500 terawatt hours in our winter season, which then gets recharged then when the spring comes. Now, 500 terawatt hours is a lot of energy. And just to give you a scale, we talk a lot about the use of electrical batteries for grid storage. As of today, that's good for about 0.002 terawatt hours. Now, we have a lot of hope for our battery technology, but there is a lot of scale up to do if that's what you want to rely on. We're talking about factors of something like 100,000. So I think our natural gas system is going to be with us for a while. We're going to have to learn to live with it in ways that are as environmentally compliant as possible. So I just want to emphasize how serious this methane problem is. You might have heard about it. It's a truism that methane is the second most important greenhouse gas, but actually that sort of understates its importance. And just to emphasize that, I've done a calculation. This is based on equations that you find in the last IPCC report. And what I've shown here is the effect of a 1 year's pulse of anthropogenic carbon dioxide, 35.8 gigatons, and that's shown in black. So once you put carbon dioxide in the atmosphere, it stays there for a long time. You get a lot of temperature change. I also showed a 1 year pulse of anthropogenic methane. That's about 335 megatons. As you see, over the next decade, the methane effect is as large as the carbon dioxide effect. Now, the methane effect does go away because methane has an atmospheric lifetime of about 10 years. But still, the methane is such a more potent greenhouse gas than carbon dioxide. It's about 100 times more potent in terms of its radiative efficiency, that they have comparable temperature effects for the next 10 years given a 1-year pulse today. So to call methane second most important, I don't know. I'm going to call it equally important. Now, we have a new estimate just came out a couple months ago about where methane in the atmosphere is coming from. As I said, it only has a 10-year lifetime, so it's continually being recharged. About half of methane comes from natural sources. That's shown by the green segments of the pie chart, wetlands and other sources. Of course, you have swamp gas and so on. Not much we can do about that. There's a very big chunk from agriculture, coded in blue. That's predominantly livestock, feedlots and so on, plus rice cultivation. A big chunk comes from landfills and wastewater uses and other waste uses that generate methane. Coal has a section, but oil and gas has a pretty significant part of the picture shown in red. It's good for about 84 megatons a year, according to the latest estimates. So, and people have sort of identified oil and gas as sort of the low-hanging fruit on this picture because the oil and gas industry actually sells gas, makes money from it, so it seems logical they wouldn't want to waste it. That is generally true. But nonetheless, that's the piece we're going to focus on. But I do want to emphasize that to solve our methane problem, we also need to attack the other anthropogenic sources and hopefully someday the natural sources. So this just gives you a sort of another picture of the role that methane has in global climate change. Again, horizontal axis in years from 2010 out for 60 years. Vertical axis is temperature change since the 1890-1920 baseline. These calculations were done by Drew Shindell, published back in 2012. So the changes that he's talking about sort of are assumed to start in 2012. The red line is his reference case, which corresponds to the International Energy Agency stated policies scenario, what's called the STEPS scenario. And that's and honestly, we're not doing as well as that scenario today. So the actual temperature change is above that red line, unfortunately. Now, if you implement Drew Shindell's CO2 reduction program, which generally corresponds with the IEA 450 CO2 equivalent scenario, you get the blue line. So you start reducing CO2 right away, but because CO2 is sort of an accumulative sort of greenhouse gas, you don't really start seeing big effects for several decades to come. And that's the blue line. Now, eventually we're going to need to control CO2, but in terms of prompt effect, something if you're going to be worrying about what's happening in 2050, it's not going to do the job. On the other hand, methane, CH4, does the job right away because it does decay from the atmosphere quickly. And here we've taken, again, Drew Shindell's prescription, a 40% reduction of anthropogenic methane versus the reference case. That means that almost all of oil and gas emissions are eliminated, plus a bunch from agriculture and landfills. That gives you an effect right now. And so that's what we really need to, if we're going to have any influence over temperatures in 2050, and as you know, the latest IPCC target is a 1.5 degree C limit by 2050. So we need to start doing stuff right now, and methane is the way to do it. Now, there are easy and hard pollution detection problems. And coal is one of the easy pollution detection problems. So here you see a pile of coal, 2 workmen standing on the top of it. This coal is probably going to be burned in an electric power plant. We know what the heat content of the coal is. We know what the efficiency of the power plant is. We know to probably within a few percent how much carbon dioxide we're going to get out of that pile of coal. And that's generally true of carbon dioxide emissions in general. We pretty much know how much anthropogenic fossil carbon dioxide we're putting into the atmosphere because carbon dioxide is being produced in beneficial processes. It's being produced to produce power, to produce cement, whatever. So we pretty much know what we're up against. Pollution control in the natural gas sector is hard because nobody releases methane into the atmosphere for beneficial purpose. It's all accidental or stray gas, leaks, whatever, uncontrolled landfill facilities and so on. So we have a much poorer idea of exactly how much natural gas we're putting into the environment. Now, in the natural gas energy system in particular, it's really a problem because whereas we only have about 380 coal burning power plants, we have 1 million producing oil and gas wells. We have hundreds of thousands, actually millions of miles of distribution pipeline. We have thousands of compressor stations and other facilities. So you're talking about everything on the millions of scale. And this is just the United States. So for the rest of the world, multiply that by a large factor. So there's a lot of places that we could be losing methane from, and we're going to have to track it down everywhere. That's hard. It's also hard because EPA regulations as they currently exist are extremely restrictive. And Murray mentioned this briefly. I'm going to go into it in a little more detail. There are leak detection and repair rules, which were promulgated in 2016, world's first methane control rules. They were just modified yesterday, August 13th. And I'll talk a little bit about that later. But what exists now is that our leak detection and repair rules are device directed. They look at a specified list of components. The list is limited in scope and limited by the age of the facility. We're only permitted to inspect facilities that are new, that have been built in the last 5 years, whereas it's well known that there's plenty of leaks coming from old facilities. Okay, too bad. There are 2 and only 2 approved leak detection methods. One is shown in the lower left. Here I am implementing method 21. Do not ask me about the other 20 methods, but method 21 is a sniffer. You have to put a probe basically right up to your flange, your valve, your connector, and see if any methane's coming out. I can tell you from firsthand experience that this is extremely tedious and not always very effective. The other method is the optical gas imaging camera. This is not the same thing that Murray talked about. I'm going to talk about the differences in a few minutes. This is an infrared camera and costs about $100,000, much more expensive than what Murray was talking about. It's easier to use because it images a cloud, but only from rather short range. So the EPA mandated detection threshold is 0.03 kilograms an hour. Just to give you an idea how big that is, that's about 3 times the gas flow from your home water heater pilot light. That is a very low flow by anybody's standards. Now, of course, our pilot lights in our water heater at home are lit, so we're not venting methane into our homes, thank goodness. But this is basically a very low leak threshold. And therefore, the camera that you see on the lower right is only useful to about a 4-meter range, 12 feet. Now, there are other ways of going about this. And this is a facility level aerial survey of the Permian Basin undertaken last year by Kairos Aerospace. Kairos flew about 30,000 square kilometers. They passed over 30,000 oil and gas wells, 16,000 kilometers of pipelines. They detected 821 sources that were emitting at a rate of 33 kilograms an hour or more. That's more like the flow rate of your home hair dryer. So, okay, still not that great, but a lot more than what you're getting in your home water heater. Now, I strongly urge you to go to Contributed Talk 280. Lena Berman explained this beautifully. Basically, what it boils down to is when you have aerial surveys, they're not nearly as sensitive as ground-based. In fact, it's something like 1,000 times less sensitive, but you're picking out the biggest emitters, not the smallest ones. You're finding where they are, remediating those. Elena gave a specification in the Permian Basin of something like 80% of gas comes from such emitters, greater than 33 kilograms an hour. As you'll see in a minute, it varies from place to place, but this is clearly a much more efficient and effective way of finding the largest leaks, which are the ones that are most important to remediate. Just to emphasize that, here's some data from Barnett Shale, which is the Fort Worth Basin in Texas. This is work that was done by the Environmental Defense Fund and coworkers. What's plotted here on the horizontal axis is detection threshold in kilograms an hour from 10 to the minus 2 to 10 to the fourth, 6 orders of magnitude on the horizontal axis. The vertical axis is the fraction of emissions greater than that detection threshold. So in other words, if you have a device that detects 10 to the minus 2 kilograms an hour, you see everything. Everything that's in the Fort Worth Basin. The measurements, which were done by a ground-based measurement with a Picaro sensor, for those of you familiar with that technology, is shown in the black line. The EPA specification for the 0.03 grams an hour, kilograms an hour, is shown by the vertical blue line. And the sensitivity, and so what the authors point out is that if you have a measurement that's 1,000 times less sensitive that EPA mandates in the Barnett Fort Worth Basin, you still pick up 44% of total emissions. So you have to ask yourself, do you want to go around and check every flange, every connector, every valve in a small subset of what's really out there? You're not going to get everything because you're not going to get anything that's not on the EPA list. Or do you want to just fly over it and get 44%, find the biggest stuff and fix that first? I think, and then if you take the Kairos number, you get 80% from an aerial survey in the Permian Basin. So I think there's no question that we want to be at least considering this strategy of aerial flyover as opposed to component by component checking with little probes. Now, the other benefit of aerial surveys is that they see everything, not just what you're looking for. So, for example, on the left, we have a big gas plume coming out of an underground storage facility. Now, this is exactly the storage facility, as I said on the slide, deregulated by proposed amendments. That amendment is now a final rule of the EPA. These facilities are no longer inspected. Nonetheless, they're leaking. Not a good system. We have a similar situation on the right where we have a broken gas gathering pipeline. Gathering pipelines have never been regulated. So no one would ever go out to this and see if there was a leak, yet there's a mammoth leak there. So these are examples of when you have an aerial survey, you fly over everything, you see everything, not just the individual flanges which are on your checklist. So this is a major advantage of having this kind of broad scope survey. It gets more interesting when you get into the realm of satellites. So there is a satellite launched by the European Space Agency, TROPOMI, on Sentinel-5P, methane sensor. It basically covers the entire world every day at 1:30 in the afternoon. If it's 1:30 where you are, just look up in the sky. TROPOMI is above you. It's a sun-synchronous satellite. Although it cannot see through clouds, which is a big limitation. Now, it wasn't designed, TROPOMI was not designed to be a point source detector of methane. But there's a company in Kairos, another Kairos, spelled differently and in Paris, which analyzes TROPOMI data to look for point sources of methane, and its sensitivity is another 3 orders of magnitude lower. We're not looking at 30 grams an hour, we're not looking at 30 kilograms an hour, now we're looking at 30 tons an hour, more or less, and we're seeing emitters everywhere. Now, Kairos says that at any one time, they see about 100 emitters greater than 10 tons an hour, of which half come from oil and gas facilities. And they can tell because they've geolocated their targets. So about half of this is oil and gas. Wow, this is, it's breathtaking. And clearly, if we have a methane problem, this is what you need to deal with first. So we have leaks at all scales. We are only focused, tightly focused on the very smallest scale. Doesn't make a lot of sense. So just to sum up the first half of the talk here. We don't know how big our methane problem is, nor what the most important sources are. Nobody knew about these massive number of huge sources until TROPOMI was launched. Logically, we should be devoting resources to finding, characterizing, and fixing the largest emitters, not the smallest ones. And this is ironic, neither aircraft nor satellite surveys can be approved as valid methods for leak detection and repair under current US Environmental Protection Agency regulations. Now, as far as the regulations that I made this slide before yesterday, we are still puzzling out what the new regulations provide. There's some opinion that they are not that much of an improvement over what we had, but that's still to be analyzed. But nonetheless, regulation has not been technology friendly. So let's look at this question of validating new technology for regulatory purposes. And I'm going to compare sort of what was in the 2016 rule, which applied until yesterday, compared to what we consider a better method. And this is documented in comments that I've made to the Environmental Protection Agency, cited in the box at the bottom of the slide, and also some work that was done with Drew Pomerantz, Kate Konchnik, and Romany Webb that we proposed for amendment, which we hope is going to be incorporated into the Clean Energy Innovation and Deployment Act, which was just introduced in Congress this year, and presumably will be reintroduced next year. So in the 2016 rule, the focus of effort was on components, the individual flanges. A better method is to look at facilities or groups of facilities, as we saw with the aerial and satellite surveillance. In the old rule, applicants for approval of new technology was only owners or operators of facilities. In other words, the guy that owned the well had to apply for approval of new technology. But what do these well owners know about aircraft or satellites? Basically nothing. The new method, and this is incorporated in the new rule that came out yesterday, is that inventors, manufacturers, or indeed anyone can apply for approval of new technology. That is an improvement that we're now seeing. Validity in the 2016 rule, single site. In other words, if you're going to fly your satellite, you have to get approval for every single individual site. Crazy, nuts, totally nuts. A better method is multiple and universal validity. And that seems to, well, we're not quite sure how that fits in the new rule. It's 609 pages long. I've only read 6 pages of it. I'll get back to you. Validation in the old system was on-site comparison with old tech. So in other words, you need to have somebody going around with your sniffer or your camera and compare with the satellite. Doesn't make sense. A better method is to use test centers that emit known amounts of methane at known rates, and you can have satellites flying over them, airplanes flying over them, trucks running around them. These test centers are really versatile. Then you upscale to the industry with modeling. And the test centers and the modeling already exist. Their role in the new rule, I must say, is something that we are internally debating about. It's not clear. Finally, the criterion for approval is that the sensitivity has to be greater than present techniques. Now, I'm an instrument builder and I love sensitive instruments, but the one thing we don't need in this field is more sensitivity. The 0.03 kilograms an hour is more than good enough. What we need is greenhouse gas reduction, and it doesn't look like the new rules do that, or at least pay enough attention to it. So I'd just like to focus on one aspect of the deregulation of methane emissions, the 2019 deregulation proposal, which was that, and this has survived in the final rule, is that methane emission control was deemed redundant over volatile organic compound control. Drew brought this up in the questions in the last talk, and now I'm going to talk about it a little bit more. The second, another aspect of the 2019 deregulation, which we've now just seen come out, is that transmission and storage are excluded from regulation. Well, we've already seen examples where that is clearly a bad idea. So nonetheless, that has survived and is now in law. But let's focus on point one. So I worked with Drew Pomeranson on this. These changes to EPA regulations can be very technical in the sense that they have manifold legal, environmental, economic aspects. And Drew and I are hardware guys, we're scientists. So we decided to focus on what we knew best, which was the technology piece. And what we asked ourselves, and in essence asked EPA, was whether their statement that methane controls and VOC controls are redundant. Is that a true statement? What we found is that for currently approved technologies, the sniffer and the camera, as commonly implemented, EPA's statement is valid, that methane controls and VOC controls are indeed redundant. However, for newly developed technologies, such as MURI's, such as the airplane, such as the satellite, that have the potential to significantly reduce the cost of compliance for regulated entities, the statement is invalid. So this is a pretty technical audience, so I'm going to explain in detail why. Basically, in the upper left, you see the infrared response, the infrared spectrum of methane at the top, propane at the bottom. Propane is sort of our model volatile organic compound. The infrared camera that I showed you, this is not like MURI's, this is narrow band. This is a broadband instrument, kind of 3.3, 3.5 microns. Picks up both the narrow methane line and the broad propane line, doesn't care, its rough sensitivities are kind of comparable. And so indeed, if you use the optical gas imager, the one that's been approved, it doesn't care whether methane's coming out of the pipe or volatile organic compound coming out of the pipe, both work fine. Okay, that's great. But this kind of broadband instrument cannot be used in MURI's LDAR instrument. It can't be used on aircraft and it can't be used on satellites. You need narrowband spectroscopy, which is insensitive to volatile organic compounds. And let's do a careful look at the infrared spectrum here on the lower right. The infrared spectrum of methane in the infrared band is shown in blue. and you've got these nice narrow lines. Now, that's really essential because if you're at 4 meters, okay, fine, you don't really care, you're just imaging a cloud. But if you're at 1,000 meters above ground level, which you are in an aircraft, or 800 kilometers above the ground, which you are in the satellite, what you need to do is you need to use a narrow band infrared method that is sensitive only to the methane line, and then you need to use a very closely spaced adjacent wavelength that is insensitive to methane. And the reason is that over these long path lengths, whether they be 1 kilometer or 800 kilometers, there's a lot of interfering effects. So you need to correct for the albedo, the reflectivity of the ground. You need to correct for dust, water vapor, all these things that are normally in atmosphere. And you need to do it in 2 closely spaced wavelengths, which you can do with a methane spectrum because the line is very sharp, nearby wavelength, no sensitivity to methane, all good. Great methane detector. It's also true of carbon dioxide and similar small molecules. However, volatile organic compounds are bigger molecules with much more complex infrared spectrum. And that's exemplified by N-butane, 4 carbon atoms in a straight chain, shown as the green spectrum on the lower right. And there you can see that if you want to look at N-butane at a individual wavelength, there's no nearby wavelength where you don't get a butane signal, so you can't do that subtraction between wavelength sensitive to analyte and wavelength insensitive to analyte. Just can't do it. So that's why VOC is, you can't really do VOC from these laser or aircraft or satellite type measurements. So our conclusion is that the deregulation, the methane deregulation, which is now in law as of yesterday, perversely discriminates against cost-effective technology. It is really perverse. So I just want to give you the reference for the new law, came out yesterday. I think perhaps the EPA timed it in coordination with this talk, maybe, but maybe not. Anyway, they've given us 600 pages to read. I'm about 6 pages into it, so you're not getting a very deep analysis of what they've done. They seem to have improved some things, but not others. Come back later for more details. I'd just like to close with a slide which I've actually showed people in the European Union who are concerned about their new methane emission regulations. Basically, on the left is present practice, as practiced here in the good old USA. On the right is what we consider a better approach. So in present practice, the objective is to eliminate all leaks at new wells and compressors, no matter how small they are. A better approach is to make the objective reduction of total methane emissions, no matter where it's coming from. In present practice, the method is component level inspection of some wells and some compressors. A better approach is all infrastructure screened by mobile platforms or permanent sensors. And by permanent sensors, I'm thinking about something like what Murray Reed showed in the last talk, where you have a sensor, you know, if it's really going to be below, say, 10,000 pounds in the few thousand pound range, $3,000 range, that means that you could start really thinking about installing them permanently. Whereas the infrared camera that's presently used, the $100,000 camera, it's not economic. So there's lots of permanent sensor concepts. I think we just saw one in the last talk. There's others out there as well. In present practice, semi-annual inspections which miss intermittent sources. And we know that intermittent sources are some of the largest sources. They're the unlit flares, the giant emissions that get caught before the next inspector comes around 6 months later, and so on. What we need is permanent methane sensors of the type that you saw in the last talk. We could also use just simple electromechanical sensors that look to see if tank hatches are stuck open or flares are unlit. And those are the two of the largest sources of methane emission from the oil and gas sector. They are considered best practice, but they are not in regulation, and certainly not enforced, because we have unlit flares and stuck tank hatches everywhere. Finally, in our EPA regulations, there was no realistic path for approval of better methods of emission detection. What we need is really to encourage continuous improvement of methods coordinated perhaps with improved emission goals. I think that's really where we need to be going. I'd just like to close by pointing out to you that there's really some terrific oral presentations in the geoenergy development and emission mitigation section. Look in your program. The three that are highly relevant to what I just talked about are shown here on the list, 51, 123, and 280. They are all outstanding presentations, as are the others in this session, and I certainly commend those to you. So with that, I'm looking forward to the questions. If you wish to contact me, my email address is on the slide here, Robert at robertkleinberg.com. Always happy to discuss my very favorite subject. So thank you very much.
Thank you very much, Bob. We've got a couple of minutes and a couple of questions, so we'll get right to them. So first question was about going beyond the oil and gas industry. And the question talks about emissions from livestock. Do you have any comments on how to deal with emissions from livestock, or I'll say from agriculture in general?
Let's see. Sorry, I've got my slides a bit messed up here. Let's get back to the screen. Here we are. Okay. Livestock. Yeah, you know, livestock, that's a really good question because I always thought that, you know, okay, so cows belch methane. That's sort of the main route. There's also a manure management issue. And I always thought, well, gee, we know how much methane is going to come from a cow. You multiply the number of cows, there you are. That turns out not to be true. There's large discrepancies in the amount of methane emitted from cows, depending on what they're fed, how they're treated, what kind of circumstances they live in. Certainly we need to do better in the agriculture domain. And people are looking at this seriously in Europe about, okay, what do you feed cows to minimize methane? How do you avoid generating a lot of these problems? And feedlots are a great way to generate a lot of methane problems. So I think that in some more forward-looking jurisdictions, there might be some motion on that. I don't see much happening in the US, honestly. You know, we like our hamburgers, I guess.
I will point out, you can now go to Burger King and buy yourself a low methane hamburger.
Well, you know, I actually have tried the Impossible Burger, and it's not bad.
Yeah, but not just a non-meat burger, but a meat burger made from low methane.
Low methane burger. Wow.
There you go. Okay. Next question. This one talks about super emitters. So it says, what magnitude of leak is economic to fix? And in the case of super emitters, are the leaks usually coming from a single point source or multiple sources that are on the same site?
Yeah, that's a good question. They are, okay, let me just give you some examples of super emitters. So like I said, the unlit flare is a huge source. So that's a single point source situation, which could be remedied by doing nothing more than putting a heat sensor at the top of the stack and just seeing whether it's lit. Another big one I mentioned is the stuck tank hatch, which again is a point source sort of thing. So I think in the oil and gas, and you tend, if you go to one of these talks that I pointed out by Daniel Veron, you'll see that he identifies some point sources that were tracked down to really individual facilities and probably individual components in those facilities. So it's very much a point source sort of thing, which should be easy to remediate. I'm sorry, did that answer the question fully?
I think it did. I'd like to move on to the next one. I think you've inspired some folks into getting more into the political realm. So the question reads, is there room for outside input in crafting regulatory policy? Basically, is there a pathway for influencing regulatory policy with this type of fact-based analysis?
Well, Drew, you know the answer to that as well as I do. What we've done is we have responded to EPA proposed rulemaking. And there is so when you implement a rule or change a rule, the procedure is about the same. It's controlled by the Administrative Procedure Act. there's a notice and comment process where an agency will publish a proposed rule and then give the public typically 60 days, something like that, to comment. And the same thing happens at the state level. So states will publish a proposed rule, then give maybe 30 days comment period where you can sort of throw in your suggestions. Now, a very interesting question is, do the agencies actually listen to these to these submissions? And that's something actually that is a area of research for me. And I'm going to be using this final rule that came out yesterday to see how well the EPA responded to the 500,000 comments that were submitted in connection with this proposed rulemaking. Now, of the 500,000 comments, really only about 100 are substantive, so they really don't have to seriously read 100. But that's a question that I think needs to be answered, and I'd like to answer it. And I'd like help, by the way, in case anybody is interested in helping.
Very good. We've got two related questions talking about blind spots for the satellite. So the first asks about, in general, if you can comment on methane emissions from offshore operations like the Gulf of Mexico. Yeah. And the second one pointed out that the TRPOMI data didn't identify very many methane emissions in Africa, and wanted to know if you thought that was realistic.
Right. Okay, so first question. As far as offshore is concerned, yes. Generally speaking, anything over water is a blind spot because water is a very poor reflector of infrared. It's a great absorber of infrared and a poor reflector. Now, I'm going to put a little asterisk on that because what people do, this is very sophisticated, they'll look at glints, which are the special angle where you get spectral reflection. It's a refined technique, so I'm not going to say you never get any information over water, but generally speaking, these satellite surveys give you just blank over anything, and that's oceans, lakes, rivers, whatever. So that is a blind spot. If we're going to do offshore, we're going to do it differently, probably with drones flying around and not using the water surface as a reflector. Let's see, the second part of the question was Africa. You know, not much oil and gas facilities in Africa. I don't really have an answer for that. And again, half of what they see is agricultural. That's rice and cattle and cattle feedlots. And I'm not enough of an expert on African agricultural economy to really say whether that's prevalent or not. It may not be.
Then we'll go to the last question here. So you mentioned, so this is about flares. You mentioned unlit flares are a significant source of methane emissions, and unlit flares do not require fancy technology to be detected. So why are there unlit flares? Are operators leaving flares unlit on purpose to avoid flare limitation regulations?
I don't think so. Honestly, I don't think so. I just think that the way of igniting and keeping flares lit is just inadequate. No, generally the operator will want to burn natural gas because natural gas is an explosion hazard. I mean, at some level, you wouldn't do it on purpose. And anyway, operators have other means of underreporting their flaring. they can do it on paperwork, which they do, unfortunately. But no, flares should be lit. You have state regulations that mandate that pilot lights be monitored. That would be a good thing. Flares sometimes get blown out when you have just like the gas is too low BTU content. You know, these are problems, but they're solvable technical problems, and they should be solved.
Thank you very much, Bob. Another excellent presentation and also right on time.